In this video, we are going to see about N-type semiconductors. So semiconductors can be classified as intrinsic semiconductor as well as extrinsic semiconductor based on their purity. Here the extrinsic semiconductors are classified as N-type semiconductor and P-type semiconductor based on the dopant. In this class, we are going to see N-type semiconductor. When the pentavalent impurity atom like bismuth, antimony, phosphorus added with the pure semiconductor, we can get the N-type semiconductor. Here N-type semiconductor means the charged carriers are negative charge carriers, that is electrons. That's why it is called as N-type semiconductor. So this is the energy level diagram of N-type semiconductor. Here valence band, conduction band and donor energy level. The excess of electrons, that is the electrons generated by the dopant atom. Actually the dopant atom, that is the pentavalent impurity atom has 5 valence electron. So out of that 5 valence electron, 4 valence electrons are formed with the parent element by covalent bonding. Then another one electron is left free. That electron is called as free electron. That free electrons are located in the energy level just below the conduction band. That energy level is called as donor energy level. So in this type of semiconductor, the concentration of electron is more than that of holes. This semiconductor is called as N-type semiconductor. Here the electrons are the majority charge carriers and holes are the minority charge carriers. Let us derive the carrier concentration in N-type semiconductor. So in this energy level diagram, we can see the Fermi level of N-type semiconductor is located in between the conduction band and donor energy level at 0 Kelvin. When the temperature increases, the electrons from the donor energy level goes to the conduction band, creating a vacancy at donor energy level. Let us consider Nd is the number of donor atoms per unit volume of the material and Ed is the donor energy level. So at 0 Kelvin, I have already said the Fermi energy level EF is exactly lies between Ec and Ed. So at very low temperature, some of the electrons may go from donor energy level to conduction band. When increasing the temperature, more and more number of donor atoms get ionized and the density of electrons in the conduction band increases. Let us assume Ec minus Ef is more greater than KT. The density of electrons in conduction band can be written as Ne, that is number of electron, which is equal to 2 into 2 pi me star Kt by h square whole power 3 by 2 exponential of Ef minus Ec by Kt. Let us consider Nd is the concentration of electrons in donor energy level and the density of energy state Z of Ed dE, which has the energy Ed below the conduction band. If we assume Ef lies more than few Kt above the donor energy level, the density of donor impurity Nd star, which is equal to Nd into 1 minus F of Ed. We have already said the density of electrons in conduction band equal to density of ionized donor in donor energy level. So at very low temperature, the Fermi-Dirac distribution function f of Ed is equal to 1 by 1 plus exponential of Ed minus Ef by Kt. So we can calculate the density of holes in donor energy level, that is 1 minus f of Ed is equal to exponential of Ed minus Ef by kT divided by 1 plus exponential of Ed minus Ef by kT. Here Ed minus Ef is negative, then exponential of Ed minus Ef by kT very lesser than 1. So in the equation we can neglect the exponential of Ed minus Ef by kT in the denominator. So the equation 3 can be written as 1 minus f of Ed is equal to exponential of Ed minus Ef by kT. So we can substitute this value of 1 minus f of Ed in equation 2. We can get Nd star is equal to Nd into exponential of Ed minus Ef by kT. So at equilibrium condition, the density of electrons in the conduction band equal to the density of ionized donor in donor energy level. Therefore, we can equate the equation 1 and 5. So by substituting the values of Ne, density of electrons, from equation 1, and Nd star, density of ionized donor, from equation 5, by simplifying this equation, we can get the Fermi energy level EF. EF is equal to EC plus ED by 2. So this is the value of Fermi energy level at 0 Kelvin. So from this equation, we can conclude the Fermi energy level lies between conduction band and donor energy level. So from this equation, we can derive the density of electrons in conduction band. So we know the density of electron Ne is equal to 2 into 2 pi Me star kT by h square whole power 3 by 2 into exponential of Ef minus Ec by kT. So from the equation 6, we can take the value Ef and substitute this equation. So we can get Ne is equal to 2 into 2 pi Me star kT by h square whole power 3 by 2, then exponential of Ec plus Ed by 2 plus kT by 2 log of Nd by 2 into 2 pi Me star kT by h square whole power 3 by 2 minus Ec by kT. By simplifying, we can get the density of electron Ne is equal to 2Nd whole power half 2 pi Me star kT by h square whole power 3 by 4 exponential of Ed minus Ec by 2 kT. So this is the expression for density of electrons in conduction band.